Okay, everyone. Welcome to the session 2. Now, today we are doing something called tokenization. So yesterday we talked about data cleaning, and today we are talking about tokenization. So after you have a lot of text, of course, you clean it up, you apply all the techniques like stemming, lemmatization, all, either lowering it, handling numbers, handling emails, handling URLs, and different things I talked about. Now, today, after you have a clean text, then what is happening inside the entire process, and why is tokenization so important? So today's lecture will be based on tokenization, and also some parts will be on converting it into features. So what is tokenization? So first of all, tokenization is a process of breaking your text into smaller and manageable units. So means tokens always doesn't mean that your blob of text would be converted into words. Intuitively, we think that tokenization means that you have initial text and that would be converted into small words. However, here it can be different. It can be converted into small words, small sentences, small characters, or you can customize it. Okay. Somebody else is trying to join. Okay. Somebody else. What? Someone has logged twice, I think. Right. So tokenization means breaking down your text data into smaller units called tokens. And these tokens are the building blocks of your entire process. Right? Now, on screen, there are different examples as I talked about. So there are different types of tokenization we have. We have word tokenization, we have sentence tokenization, and then we have here word tokenization, sentence tokenization, and subword tokenization. So this small concept that we always have, even I have, that text is always split into words that needs to be addressed really well. Text is not always split into the words. It can also split into sentences. It can also split into smaller units. So all these things on your screen are the example of tokenization. Now here you have an example. The quick brown fox jumps over the lazy dog. Now you see that here each word is converted into small token. And here, D is one token, quick is another one, brown is another one, fox is another one. And all these things are tokens. So now here in the sentence example, this is the first sentence, this is the second sentence. Now, this is the first sentence is token 1. And this is the second sentence is token 2, right? And then you can also have, in a lot of cases, you can also have tokenization based on subwords. Here you have three tokens, token 1, token 2, and token 3. Now, you won't believe that 90% of the time, we are doing a lot of subword tokenization. So I would talk in the following presentation is what is something called embeddings by BERT model. And there we do a lot of subword tokenization. In the past, when we were still developing all these models, word tokenization used to be the number one thing. Now, having said that, let us quickly understand how the tokens are converted into features. And then we will go more into tokenization. What are the famous libraries and which we should use when? And when you Google it, why there are only 3 or 4 libraries come up. But before that, let's quickly see how tokens are converted into features. Okay. So, for example, now we have a sentence, okay? I love this movie, right? So I love this movie, and we are right now doing word tokenization. I'm not running tokenization for sentences. Now, what happens when you do word tokenization? It converts into I love this movie. So each of the word is one token. This is token 1, this is token 2, this is token 3, and this is token 4. And now you are doing some kind of sentiment analysis. You have 3 people. One of them says, I love this movie. Other says, I hate this movie. And third one says, the movie is good. So the entire 3 system, I love this movie. And then there could be 3 other sentences. I love this movie. You know, let us continue here very much. Or somebody say, I hate this movie. So love is replaced by hate. Other says it's a bad movie. So now you are doing some kind of sentiment analysis. So this sentence now, different people can have, you know, I love this movie very much. I hate this movie, and the movie is really bad. Now you see, because when you have a certain context, the entire thing, your features here, it's just an example that it will be divided like this. So we have, you know, a lot of words in the vocabulary. We also added very much. We also have hate. We also have bad, and we also have say good. So when you convert this feature, I love this movie, into this token into a feature. So now what is happening? Because all these words are also in the vocabulary. So we will have a feature like, so I love this movie in this sentence. So I am just right now converting this particular sentence into your features. I'm not converting any other. This is just my words for the vocabulary purposes, right? And when I convert it, let's see how does the feature looks like. Feature looks like 1 1 1 1 0 0 0. Now how did it become? Because I love this movie has one word, I love this movie, but it doesn't have any word as hate, good, or bad. So we have 0 0 0 that's given to those words. So that means right now I'm just providing you the example. So in your vocabulary, how many tokens you have? You have 1, 2, 3, 4, 5th token, 6th token, 7th, and 8th. Okay, very much can be one word here. Okay, I have made it hyphenated. And out of this token, so now you can have here n number of words, right? And like this, if you have n number of words, any of the sentence can be represented into this feature. So this is just giving you a sense that when we start developing, you know, these models, how things happen. Now, yesterday after the session, Tehseen mentioned to me that we have a lot of parsing issues. Sometimes, you know, when you develop very advanced applications, the solution lies in a very simple things. And it is very important to understand that every time you might not really need to apply neural nets into your projects. Sometimes things can be done really simply. And for that, it is very important to understand that if NLP cannot be done without using, you know, it can be done without using a neural network. There is a lot of technology that was developed before neural network. So some projects can be solved, and maybe you have neural networks in your pipeline, but we can add a little bit smaller part without neural network. And for that, a little bit of knowledge is required. And the idea of this activity is to train you for that. So now the main key takeaway from this slide, we all got it, right? We have a clean text. The clean text can be converted into either words, sentences, or subwords, and these are tokens. And now we are converting tokens to features. Now I gave you a small example here, very simple example, that my vocabulary only has 8 words. Now with this 8 words, if I have in my vocabulary, how a feature vector represent this? Now, same thing, I hate this movie. How will you represent I hate this movie? You will just say one. So now the sentence is I hate this movie, right? Now, this is very simple. I hate this movie will be, everything will be 1. And here love is 0, 1, 1, and hate is 1, and 0, 0. So this will be I hate this movie. So now you can see how your words are converting into feature vector. So this was just an example. Okay, let's get back. When you guys start building applications, what are the famous libraries you come across? Okay. So first of all, very important, there are quick takeaways here. Okay. So main takeaway that we have here from the slide, why tokenization matters. So tokenization matters because, you know, if you have a text, which is a continuous stream of characters, you need to provide some kind of structure to it. And tokenization imposes that kind of structure. Other thing will be, we already saw that it is with the tokens that you create meaningful features, right? You create features. So tokenization provides structure. With tokens, you can create features. And with tokens, you can do a lot of vocabulary management. For example, there are words which are love, hate, good. And how you can, you know, like in the vocabulary management, they all are, you know, going towards sentiments. All these tokens. So if this has 1, 2, or 3, so you will simply save into a category that there are 3 tokens, and you know there is a category, you know, there are sentiment. So that is vocabulary management. And the most important thing is all the models such as BERT or GPT, they rely on tokenization to break the text. So this is why, you know, tokenization is the first step, and most of the time we don't understand. And I will show you some outputs of the code that, you know, we really don't understand why this token, you know, comes like this. Okay. Okay, this is very, very important, guys. Like, this is the heart here. So on screen, you see here that when we say, I ask you to build a project, I ask you to scrape a lot of data from internet. And now I give you a task, you clean it using, you know, a lot of tips I gave you yesterday. And after cleaning it, you start to tokenize and you Google it. And there are different kind of libraries there. So the famous libraries that we have are simply white space tokenization, where you have, you know, a word. So for example, if you say that, you know, this is the word itself, tokenization in practice. So what will happen is, if tokenization in practice itself is a word, it will start breaking it from white spaces. So then there will be 2, 1, 2, and 3, you know, tokens coming out of it. So this is white space tokenization, which is done by identifying spaces. Now, after white space tokenization, I introduced 2 libraries yesterday, which are very, very important. One is NLTK, other is spaCy. And fourth is BERT. I introduced all of these 3 libraries to you guys yesterday. And for tokenization, these libraries are ultra important. Now, but there is a little difference which one to use when and why do we use it. So NLTK, so NLTK is one of the oldest libraries. And when everything started developing, we had white space tokenization developed, and then we had NLTK was the second step. NLTK, the entire library is trained on vast data. So what has happened is, so it's more, coming from, because it is trained on vast data, finally they found the algorithm the best thing to tokenize the entire Wikipedia, for example, is to maybe, is one of the things is that it identifies the boundaries correctly. It also handles your punctuation correctly. Whereas spaCy is a little bit more advanced. It came after NLTK and it is built on a statistical model, right? spaCy is built on a statistical model where it's trained on a lot of data, but there is more sophistication done. And then we have something called BERT. BERT we all know, right? BERT is a transformer-based model. It's a transformer-based model. So now we'll just dive a little deeply to intuitively build this thing that, I should use either NLTK or spaCy or BERT. White space tokenization, you can do it for very easy tasks, but you will run into issues if your text is a little bit complicated, but it will do easy thing. So when you start building it, these three libraries will pop up: spaCy, NLTK, and BERT, and you will see their recommendation all over the internet. So let us see. Okay, guys. Let us talk about spaCy a little bit more. Okay. I'm talking directly spaCy, and then I will compare it, because spaCy, you can say it is one of the standard choice. And when you think you have a lot of text, how will you break it into small words? So you have to imagine you have a text which is about 1 million words. And now those 1 million words, or you say 10 million words, how does it convert into tokens? Do you see, if I give you that much text, what you think about? You start thinking about, oh, I have a text. Where should I, how do I break it into, small chunks, you can say. So here, spaCy, what it does is, it definitely, there is a lot of things that happens with, white spacing is definitely an inherent thing, but with spaCy, you handle edge cases really well. So if you have, some kind of text which has prefix, suffix, and infix. So what does that mean? If you have a finance document, it will have $200, right? So what spaCy will do it will convert this dollar into a separate one and 200 into a separate token. And now there is a lot of, I will go in detail that, what BERT does. Now, for infixes, now somehow your tokens, so infixes would means you have hyphens, right? Email, and you have don't. So a lot of libraries will convert this don't into, don't will be one token. Your your punctuation would be another token. Then your T will be another token. So all these are tokens. So having said that, your punctuations are also tokens. So whenever you have a text like this, your punctuation also become tokens. Now here you see, spaCy handles special cases. So here you have don't, right? And anyone can, will do that. And look at here, don't his, wherever you have comma, it's a separate token. This is a token 1, do, and nt is a token 2. So this is where, spaCy treats white spaces and punctuations as separate tokens. So this is all inherent that, but when I provide the comparison, it will make more sense. So overall, from this slide, the main takeaway is spaCy is generally very powerful, and it's a statistical model that is working behind it. And it handles your prefixes, suffixes really well. And in the contractions, it separates the contractions, right? And finally, white spaces and punctuations are taken as separate tokens. Okay. Don't think, guys, this is, kind of, you will run into, a lot of things when you start doing tokenization. It's one of the problems. So now you see, I have example. Dr. Smith doesn't like visiting New York-based museums, especially after 9/11. So when you look at this text, what are the problem areas for anyone to token? So the problem area here is this dot. Most of the libraries don't know what to do with this dot. And when I have a lot of text, what I scraped from internet, then I have major problem because it contains a lot of punctuation. Now the second problem area in this text is doesn't, right? Then the third problem area is this hyphen. This is a compound word, right? Now fourth area is that this is also a compound sentence. We have a punctuation here. Then the fifth problem is we have problem here. Now all these things, now you see it's converted into tokens. Now spaCy, what it is doing is it is converted this York based, which is a compound word, into 3 words. It is taking York separately, hyphen separately, based separately, right? It keeps 9/11 as a 1 token intact, right? It also takes the punctuation, which is your last, dot here, as separate token, right? There is a separate token that comes from the comma here, right? I'm not going word by word because it becomes very boring. So these are some of the things that spaCy handles it. Now, here, however, it also takes this thing as, does not has come into does not separately. So this is a library which is really statistical based. You don't need, big computation and stuff, and reliably works better. Now let us see how is the output compared with NLTK very quickly. Now what happens in NLTK? So this is the output of same line, and we already discussed spaCy, right? So what does NLTK does? So I told you NLTK is a little bit more previous than spaCy. So let us see what NLTK does. NLTK take this thing as 1 word. This is the main difference here. So it is the compound words. So these compound words, especially if you are scraping some scientific literature, or if you're even scraping, newspaper, where we use a lot of compound words, because of, we want to convey it very, how to say, very, in very less words. When you have abstracts, when you have a news to be written in 200 words, we commonly use, something called compound words, and you will have a lot of words like this. So this is one thing. Now, so main thing that is the difference between spaCy and NLTK is that spaCy splits into 3 words, NLTK treats it as 1 token, right? So overall, this was the main difference, but the main difference is also in the computation part. NLTK is very, very easy. spaCy is a little bit more heavier to use. And then you come to the here, just a second, guys. I'll hide floating. Yeah. So what is the main thing that they tell is, okay, the diet. Okay, just a second. Annotation is gone. Okay. If I hide this, like this thing, then also the annotation panel goes away. So this is something, if anyone knows if there is a way, that would be helpful. Okay. So wherever you need to have more granularity, you have to really do more granularity, then you use spaCy. But NLTK is mostly, you can say, as a first step. So you have white space, then you just use NLTK because that library is very easy. Then for more compound words, here I am emphasizing on something, you can say, application which consists of 10 million words. So there spaCy is a good way, but let us learn about something. If you have a lot of computation, what do you use? So this is just more example here between spaCy and this thing. So what is the main takeaway? If you have easy computation, so you see it is very, very slow for larger data sets. So here everyone wants to build application. This is the bootcamp that will finally teach you how to build really industry related application. So for NLTK, if you have a lot of larger data sets, it's a poor choice. So you have to use faster, for if you really have a lot of data sets, so you have to really use spaCy. Now, you see, there is a faster performance, but what do they say? If you are building an application on abbreviation, on medical, on health records, on spatial measurements, spaCy is a bad choice. Why? Because it's just not trained on that kind of data. But NLTK is doing better. However, it is slow, right? And why NLTK is a first, like I said white space, then NLTK, because it's something that can be customized and it is still, it's very flexible. And you can use it on wide range of languages. So spaCy is only faster. They generally would result in same results, but still people, when they actually put these two libraries in application, there is a close competition between NLTK and spaCy. So you need to test it using both. But if the computation is okay for you, you can go for spaCy, otherwise go for NLTK. So these are the main things. Then also NLTK, also you can do French or Arabic with it. And they say, see, this is very important. Anyone who is from the company, they say spaCy is for industry. Anyone who says for research and education, they say NLTK is a choice. But with industry, even you put spaCy in, but then you have problems with a lot of, kind of domains here. So you have to be careful. So you have to test. That's always the case. But these are the two libraries available. Now let's talk about the third one. Okay, very good. Now see what happens, right? This is like the good part, because now, when the transformers came then in 2017, they became a big hit. But believe me, there was a lot of research happening even before that. So BERT is, we all know what is BERT. It's a transformer-based model. Transformer-based model, I hope, that GPT is a transformer-based, Claude is a transformer-based. That means it is based on very latest technology. And you can use BERT to tokenize, but that doesn't mean that it is the neural network who is tokenizing for you. So neural network is not tokenizing for you. It is, when you use this library, there is something called, byte pair encoding. There's something called byte pair encoding. That is the technology that is used. And I would give you a very, small sense of how it is working. But let us see very quickly. When you put the same sentence that, you have Dr. Smith statement that we discussed, how it is breaking it. And it is one of the advanced technology. So you see here, Dr. That is all good, Smith, but it starts breaking this into these, the words which are, like this. It start putting these kind of hashtags because you want, it's a part of the previous word. So this library is, there is a lot more work that is, done on the sophistication or the nuanced, and they have improved it. So you see here, NT, which was part of the previous one, the token comes with hyphen, right? Now here, even based, you see it was a compound word. It knew that it is coming from the part of the previous word, so I would start putting hyphens here, right? And then here, they are also able to, separate this 911 that wasn't there in the previous one. So these are little changes and they make ton of difference because the context is preserved. So when the context is preserved, you want to know that this word is related to the previous one, right? And not only that, so what it does is, there is something, if you use today BERT, you will start seeing in the tokens, there is something called CLS and there is something called SEP. So not only that, when you have the tokens, it will add here in the beginning CLS and separator. What are these two extra tokens? And if I today, ask you, go home and, start building your application using BERT, you go and you see these are the tokens that are appearing. So these are the tokens that one is in the beginning of the sentence, CLS, and separator is at the end of the sentence. And like this, so two main things that we talked about is, one is the hyphenization that is happening. So one is the hyphenization that is happening, and other one is the introduction of these tokens, where this one is the end of the sentence, and this one is at the beginning of the sentence. So this is the beginning, this is the beginning, and this is the end. So that is your hyphenization happening. Sorry, so this is the extra feature by BERT, which really makes it very easy if you have a lot of complicated words. Now, what do you see? One thing on the screen. You see here the tokens are very heavy: 101, 619, 2522, 2285. Why are these tokens? So what is happening at the back? At the back is your, 1, 2, 3, 4, like this, 2000, and here 10,000. So there we have a lot of words in the vocabulary. Now, what does BERT do? It's big library. It goes and matches the index that, doctor is at 101 word is back in the vocabulary, right? Now 2285 is the word, at the, you can say, this word visiting, maybe it's 2285, right? And this word, which is 11, is 1010 position. So it is giving you the position corresponding to what is in the vocabulary. But this is very important, guys. The CLS and SEP token, you will have it all the time whenever you tokenize it. So this is how the BERT is working. Okay. So we get the main takeaways, right? The main takeaways was simple, right? Hyphenization, CLS SEP token, then it gives you the token IDs matching its vocabulary, right? Okay, very good. I think I talked about this, but very quickly here, this is just for your reference. Provides this hyphenization, provide these tokens, and then it splits into 911. Also, it is splitting your doctor into, and which is other libraries are not doing. Now, what is the keyword here? The keyword is out of vocabulary words. That BERT is very good. So tomorrow, I create an application which also involves a lot of French word. So for example, I just say, I love cat. And, you are also promoting it, to your French market. And you just convert this into gem cat. And it's some kind of, very trendy kind of advertisement going on between French and English. So here I'm not converting cat, that is into chien, if anyone speaks French here. I'm just converting, cat, I'm keeping as a cat, but I'm only converting the first part. Now, for any library, this word will show up. They won't be able to parse it. But your BERT, this is known as OOV, that is out of vocabulary word. So what it will do is, if your campaign has a lot of, everywhere you have gem, it will, go and try to match it with its vocabulary, and, it is not able to do it. Then it will, see that this word is coming again and again, and it will try to give it, a new vocabulary token here, and, it will do some kind of mathematical modeling, or you can say some kind of mathematical model. That's this byte pair encoding. I will talk about it very in like 2 minutes, and it will put it. So BERT is ultra powerful in a lot of things. If you have the ability to do it, you do BERT. It will save you a lot of headache. I do BERT or spaCy a lot because they are faster. NLTK, I used to do it, but recently I go with the BERT as my first choice. But you should have a strong computation. If you don't have GPUs, then I'm not sure. I think then NLTK would be the choice. So overall, we got right, spaCy and BERT faster, NLTK slower, and with BERT, all these extra features, they come, right? Okay. Now, this is the summary, but what is the main thing here? So one thing is, like, NLTK is more general text. spaCy is rule-based. What is a rule-based thing, guys? Rule-based thing is that I have my own rules, that I want it to, split it in between. I don't want to split it, this thing into separate punctuation. I can create my own rules. So they have been created by looking again at 10 million data. And then with BERT, we know that this is more for deep learning and it is more fine-grained. I want to emphasize this point. Fine-grained is very important. If you are doing, really a tokenization, then it uses Subword tokenization, right? And then you have to see, this is transformer, statistical and rule-based. Now, okay. So this is the key takeaway. We already discussed it. NLTK is more traditional. BERT used is for neural networks, and spaCy is more of a balance between NLTK and BERT, which is fine. And it provides more linguistically informed tokenization. I think we got it. We got it finally, right? Okay. Now, this is for, for a little bit more about byte impaired encoding. But before we go and do the code. Okay. Code is simple, as I told you. Most of the codes, especially right now, they are simple. But believe me, the boot camps pick up very strongly from next week because this is the first week. So I don't want to build, give you very heavy codes. So right now it's an easy code. So see here, guys. What is happening here in this code? We have installed, something here, some data sets, some transformers, and some, some other library, QQQ, which is fine. But you see here, what I'm doing is, so we are importing NLTK, we are importing spaCy, and from transformers, I'm importing something called auto tokenizer. So transformers is the BERT one. I'm importing these three libraries. And then I think this is the package that I'm downloading, the punked package for NLTK. And this one is the load dataset library. So this is very simple. This is something, a function that I'm calling from dataset. So load my dataset. This is just loading my dataset. And now the dataset is about news. So I'm just giving it that load dataset, load news. And now I have started loading the news here. Now loading the news, and I'm just loading, if people knows Python here, this is my first line I'm loading, or the first news I'm loading. And here I am just loading the news here. Wall Street bears claw back into the black, rooters, short sellers, Wall Street dwindling, band of ultra cynics are seeing green again. So this is my text that I'm loading. Again, I go on Python, I import NLTK spaCy as transformer, I load a function called, which will load my dataset. And dataset that I have loaded it, some kind of news dataset. You can also, load something which is in your computer, and, you can load it, some of your favorite, storybook or some of your favorite novels. And then I am just, if my application is not huge, I will just talk about white space tokenization. And what is this doing is, it is just, so it is that simple. You're calling it, text.split, and it is actually splitting your things into, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see here, your routers, the white space is so, how to say, primitive as a library, that routers, it also has this thing, brackets, and it is just tokenizing it. like that, right? Now it's simply, a thing that white space is primitive. Now, here what I'm doing is I'm tokenizing word-wise with NLTK, and I'm also tokenizing sentence-wise. So word-wise and sentence-wise here, now you see here, I call it chunking. If you have a big text, you actually chunk, the sentence, and you chunk it, the sentence, and here, there, this is, it's, so guys, you have to see where there's a comma, it's one token. So if I go here in the sentence segmentation, the comma is here. This is, one token. Or I think it has taken it into the entire token as together. Yes, it is just taking it here. No, this one is just, so there the sentence tokenization is done only at your dot for this one, sentence segmentation. He says that it's only a one sentence, and your rule that is working is the dot. So this is totally one token, which is slightly thing. And then here you see this thing, routers. With NLTK, it started separating it into a separate thing. But because it's a router and it is repeated again and again, there is no need. It is only repeating once, right? Now for the same thing, this is now I did by, so this was white space here. This was NLTK here. And this is my spaCy here. Now with spaCy, what we do is the same thing. I don't think so there's a difference at this text between spaCy and NLTK. It's just an example. They are very similar. Yeah. But the issue would come in most of the part, it will come in the computation. And it is doing exactly the same thing. So NLTK and spaCy, they are doing very much the same thing. White space is very primitive. It's, also taking it as a separate token. Now we go to the fourth one. That is my thing. I like it. This one is a BERT. Now we have a tokenizer. That is a BERT base. So we are importing a tokenizer from a model called their base model. And then after a tokenizer, I'm trying to, print those tokens. And I'm just printing their IDs as well, right? I'm also printing their IDs. So let us see how did it token and then talk about it. So token from the beginning. So it is now added a token called CLS. Now, if you don't know how BERT tokenizer works, you will try to clean it. You say something is happening and, I need to clean this. No, this is coming from the BERT, right? And this is the token that is coming. And here we are also have their IDs, which is, I told you that, it is mapping from its vocabulary, right? So you have this, and now it is CLS and SEP, right? And so what I did is I started printing it because I could have done, I did it last night, but I could have done all, but here it is from 5. I don't run the code because then it's a longer class and it's a working day for everyone. So, but these are simple codes. When the codes become much more, how to say, complex, then I should start doing just the coding. So here, BERT, I'm just printing it from 1 to 5 just to show you the CLS. I'm also printing it from the back, if you know. This is printing it from the back in the dictionary. And this is giving me a separator, CLS and separator. And this is the BERT tokenizer. So this is how it is doing. And I am not, okay. So sentence also you can do it, but it will be the same thing with the sentence as well. But yeah, I think you should be fine because it will be separating for this sentence between the two sentences. but I haven't used it here, the case for sentence. It's just the word. Okay. Okay, guys. So I think the session was clear. And I have something more introduction about here byte pair encoding, which is not very important, but somebody who has a mindset to understand what is byte pair encoding. Basically, it's not important for your boot camp, but just it's an exercise to tell you that byte pair encoding is a process that is running inside your. There's a chat question here. Okay. Hi, Shraddha. A quick question. Do we need to do both tokenization and sentence? Kathy, it all depends on the basis of your application. You don't do together. Either you do word or you do sentence. If you have an application where the context is important, you always go for sentence. But if you have an application where word is an important thing, you do word. Something like yesterday I talked about keyword, right? That you do. Now here guys, this is byte pair encoding. Now what is happening is, so if you give, I told you an example that you have in France you have gem. So in gem it will start, it's an extra word, and it will start making a kind of repetition pattern, or you can say it will find the most repeated or frequency that is there. So if you have three words, low, lower, and newest, it is breaking into LOW, LOWER, and NEWEST. And it will count the frequency of pairs. It is saying LO is appearing twice into this entire corpus. So it is 2. OW is appearing twice, so it is 2. WE is appearing, so it is 2. So all these things are appearing too. So for example, gem cat, and this campaign is appearing again and again and again. And then we also use the word gemla, which means, I love that together. And those are the new words in your library. So it just counts it, that how many of those in those words are there sub characters that is coming twice, and it merges it together. And then everywhere the most common ones, it has it, and calculate the frequent pairs. And if it is more frequent, the out of word vocabulary in BERT, this gives a extra word. So this is just a mechanism I'm telling you, because byte pair encoding is the word that you would commonly read on internet. It is associated how the BERT is doing its tokenization very, very commonly. In Amazon, one of my clients, they had even this thing, in the parsing, they played with some of these byte pair encoding. So this, I just want to introduce you the term here. I want to tell you that in BERT we use it, and it's about finding the repetitive pattern in the new words. That is it. I think with this we can end today's session. I'm open to questions.